So we're starting lecture note 7, and this will build upon the work we've been discussing in the past couple of lectures, where we have gone through the thermodynamics of for example, ideal solutions, and then the Flory-Huggins model. And now, with that machinery in place, we're in a position to go ahead and use that for practical applications. And so the place I'd like to start, although it's not the only place this information is valuable or useful, is with discussing gas solubility in polymers. As you'll recall, the rate of transport of small molecules through a non-porous polymer depends upon the solubility of the small molecule times the diffusion. And so we will discuss in this part of the course solubility, and then later move on to diffusion and move from gas to liquid and solid-based systems like controlled drug delivery. And so we'll cover the range of thermodynamic models for describing solubility of penetrants in polymers. And beginning with the way we typically describe gas solubility is in terms of a so-called solubility coefficient, which is labeled S on this slide. And it is the ratio of the concentration of gas dissolved in a polymer divided by the pressure, or in a gas mixture, the partial pressure of the gas that is in contact with the polymer. And so we imagine a situation where a polymer film is exposed to a gas and at a given pressure, and as a result of that there is partitioning of the gas between the gas phase and the membrane phase, or the polymer phase. And after equilibrium is reached, there's a certain concentration of gas in the polymer when the pressure or partial pressure of the gas is equal to P. And as you might expect, as P changes, as you change the pressure of gas in contact with the polymer, then the concentration of gas dissolved in the polymer will also change. Historically, the way such partitioning phenomena are described is in terms of a so-called partition coefficient, which would just be the ratio of the concentration of a penetrant in one phase to that in another phase. And in fact, if we recognize that the concentration of gas in a gas phase can be obtained from the, for example, the ideal gas law, and that concentration, which would be just the moles of gas per unit volume, would be P divided by RT. So if I replace P in this expression with P divided by RT, then the ratio on the right-hand side of this expression becomes the concentration of gas in the polymer divided by the concentration of gas in the gas phase. And that would be a more traditional definition of a partition coefficient. However, historically, for gas solubility, gas and vapor solubility in polymers, we define the solubility coefficient as shown here. Often the units on concentration are expressed as cubic centimeters at standard temperature and pressure per cubic centimeter of dry or penetrant-free polymers. And cc's at STP is just another way of writing moles, because in 22,414 cc's at STP of any gas or vapor is 1 mole. So you can view the concentration here as moles of gas per unit volume of the penetrant-free polymer. Often, for example, when we're modeling transport phenomena, we need concentration in other units, such as weight fraction. And so the weight fraction of penetrant A in polymer is related to the concentration, as shown by the relationship here, where M sub A is the molecular weight of the penetrant, and rho sub P is the polymer density. And you can work out the units to see that this would just give grams of penetrant per gram of penetrant plus polymer. Another convenient concentration scale is volume fraction. And as you'll recall from our discussion of the Florey-Huggins and Florey-Rayner model, they're always expressed in terms of volume fraction of penetrant and polymer in a given situation. And so this expression gives us the conversion of penetrant concentration to volume fraction. And again, you should work through the units to make sure that that you get to a point where this is the cc's of penetrant per cc of penetrant plus polymer. And this is often written in terms of the so-called partial molar volume of the penetrant and the polymer. And we'll have a longer discussion about that a bit later once we've finished this particular slide deck. That will come in lecture number 8. We imagine the dissolution of a gas in a polymer to follow a two-step hypothetical path, and that is the gas molecules will be essentially condensed from the gas phase to a liquid-like density, and then the liquid-like penetrant mixes with the polymer segments to form the gas polymer mixture. And so the thermodynamics are a condensation of the penetrant and then mixing the penetrant with the polymer. This is a hypothetical path, of course, as the penetrant molecules from the gas phase partition into the polymer. They don't literally condense and then mix with the polymer segments, but we can break up that dissolution into these two hypothetical steps. There'll be an energy associated with each of these steps. So for the first step, the energy is the energy associated with condensation of the penetrant, and for the second, it's the energy associated with mixing of the penetrant with polymer segments. And in a preview of what we're going to see in just a moment, the energy associated with this first step is often vastly larger than that associated with the second step, and that has very practical consequences for gas and vapor solubility in polymers, which we'll go over in just a moment. This is also the mechanism by which one might view gases as dissolving in liquids. So, for example, oxygen dissolving in water could be viewed as the same sort of process, and it highlights the similarity between gas dissolution in liquids and gas dissolution in polymers, and we'll see that come up again here in just a moment. By way of practical matter, for many light gases at low pressure, things like hydrogen, helium, methane, nitrogen, and so forth, often the so-called sorption isotherms, or the relationship between the concentration of gas dissolved in the polymer and the pressure of gas in contact with the polymer, these sorption isotherms are often linear. And a simple model of that is that the gas concentration in the polymer is equal to the pressure or partial pressure of the gas contiguous to the polymer times Kd, where Kd is a Henry's law constant. So this just reflects a linear relationship between the gas pressure concentration of gas dissolved in the polymer. If you double the pressure, you double the amount of gas dissolved in the polymer. We can write this in terms of the solubility coefficient. If we remember, the definition of solubility is gas concentration divided by pressure. And in the case where the sorption isotherms obey Henry's law, then the gas solubility is just a constant. It's the Henry's law constant. And implicit in this discussion is that Kd is independent of P. And it will depend upon temperature, it depends upon polymer, it depends upon the penetrant, but it's independent of pressure. And with a number of polymers and penetrants, particularly those in which there are no specific strong interactions between the polymer and penetrant, there's often a really good correlation between solubility and boiling point or critical point temperature. And that's being shown here in very old work from Van Amerongen, which is plotting the solubility of a variety of gases in natural rubber, which is cis polyisoprene, at 25 degrees C. And you can see that the open circles here are solubility plotted as a function of a normal boiling point. That's the boiling point at 1 atmosphere. And as the boiling point increases, the solubility goes up. And this is a logarithmic scale for solubility. So solubility goes up exponentially as the boiling point of the solvent goes up. And the way you want to think about this is that as the boiling point of the penetrant increases, that reflects stronger and stronger interactions between the gas with itself, and that then correlates well with higher and higher enthalpies of vaporization. Essentially, delta H of vaporization, which is a dominant energetic contribution to this first step in solubility. Delta H of vaporization typically scales with boiling point. The higher is the boiling point, the higher is the delta H of vaporization, the stronger is the interactions between the penetrants that keep them, that want to keep them together or want them to condense if they're in a gas phase and not condensed. A related correlation, which is I find very useful, is critical temperature, and solubility often scales very well with critical temperature. Both of these correlations show an almost straight line relationship between solubility and critical temperature. And as we'll see in just a moment, critical temperature is another indicator of the condensability, if you will, of a gas. Like the boiling point, the higher is the boiling point, the more condensable the gas is. That is, at ambient conditions, high boiling point materials condense readily. Low boiling point materials do not. Similarly, high critical temperature materials have high solubility and high condensability, and low critical temperature materials have very low condensability and then low solubility in rubber, in this case isoprene, but also in other polymers and in liquids. And just as a reminder, the critical temperature for any compound is a molecular property of that compound. It is the temperature beyond which the material can no longer be condensed, that's above which it's a supercritical gas or vapor, below which it can undergo a phase transition between gas and a liquid state. And to rationalize this relationship Some time ago, Alan Michaels, who's a leading figure in this field from the 50s and 60s, put together the derivation I'm about to go over with you, at least rapidly, to help rationalize the correlations that we've seen on the previous slides. It begins from the point of view that at thermodynamic equilibrium, the condition for thermodynamic equilibrium is that the chemical potential of a penetrant in a gas phase is equal to that in the polymer or dissolved phase. And it is this equality of chemical potential that is the definition of thermodynamic partitioning between two phases. And if we write as Michaels did the chemical potential of the gas at its boiling point relative to its chemical potential at a standard state, temperature T and pressure P star is the vapor pressure of the polymer at that temperature. So this is our reference state for chemical potential in this calculation. We can write the chemical potential in terms of the reference value plus RT times the logarithm of the activity, and that is the pressure divided by the vapor pressure. And in the polymer phase, the penetrant chemical potential for a rubbery polymer could be written in terms of the Flory-Huggins equation that we talked about last time. And so the expression for the chemical potential of the gas in the dissolved phase at the boiling point of the penetrant, pressure P, relative to the reference conditions, and I need a P star here to make this compatible so that we have the same reference state in both for both the gas and the dissolved phase. And so this is the expression for the logarithm of the or for the chemical potential of a penetrant in a polymer. You'll remember from the Flory-Huggins expression, phi p is the volume fraction of polymer in that mixture, and so 1 minus phi p is the volume fraction of penetrant. And the chi here is the polymer penetrant interaction parameter. The volume fraction, as we've just seen, can be written in a volume fraction of penetrant can be written in terms of the volume fraction of polymer, and that is given by this expression, which we just showed a few slides ago. At low levels of gas uptake, the term here in the denominator, gas concentration times partial molar volume divided by this conversion factor in cc's at STP per mole, at low concentrations of gas in the polymer, this term will be small relative to 1. And this is often the case we observe for gases dissolved at low to moderate pressure in rubbery polymers. And we can approximate then the volume fraction as being given by this expression. We then put that result back in the expression for the volume fraction of solvent that appears in the Flory-Huggins equation, and we get this result, which we'll use here in just a moment. And so we can write the chemical potential of the penetrant in the dissolved polymer. Again, there should be a P star here, and we've related the 1 minus the volume fraction of polymer, which is the volume fraction of penetrant in the polymer. We've related that to the concentration of gas in the polymer, partial molar volume, in this conversion factor. And we now load this expression into the expression here, and after a bit of algebra, we get the result that's shown in the middle in the middle of the slide. And to complete this analysis, we need an expression that links the vapor pressure to physical properties like critical temperature or boiling point. And the Clausius-Clapeyron equation provides a route to that equation. It says that the change in the log of the vapor pressure for any material divided by 1 over T goes as minus the negative of the delta H of vaporization over the gas constant R. And so this expression can be integrated, assuming the delta H of vaporization is constant over the range of temperature that is considered, to get the relationship at the bottom of the page. Michaels related the delta H of vaporization to the delta S of vaporization using the thermodynamic result that at a phase transition from gas to liquid or from liquid to vapor, the difference in free energy between those two phases is 0, and so that allows one to write the delta H of vaporization as the boiling point times the delta S of vaporization to get the result that Michael showed at the bottom of the page here. And now combining these two equations gives an expression for the chemical potential of the gas, now related directly to the boiling point of the penetrant. And we have the expression derived earlier for the chemical potential of the penetrant in the polymer that is shown here. And if we combine these two expressions and enforce the equality of chemical potential in the gas and vapor phases, we get the result that's shown here. We can isolate the expression for the concentration of gas in the polymer, and now we start to see that the log of the concentration can be written as a linear function of the boiling point. And if the delta S of vaporization is approximately constant for a variety of penetrants as they undergo evaporation, then we can see that indeed this would give a linear relationship between the concentration of log of the concentration or log of the solubility of the gas with a measure of condensability like boiling point, because the rest of these terms would simply be either constant or would vary little from penetrant to penetrant. Now, C in this expression is the concentration of gas dissolved in the polymer at 1 atmosphere. And so numerically, C will be equal to S, although the units on C and S will be different. Units on C are cc's of gas at STP divided by cc of polymer, and then on solubility will be the units on concentration divided by pressure. And so we can reduce this expression to the following form when we just combine all of the terms that don't have the boiling point into B, and we write this term as A. And in most cases, we typically treat A and B as adjustable constants for a given polymer. And so this particular correlation that was derived by Alan Michaels is written in terms of concentration and normal boiling point. However, C in this equation is often replaced by Kd or solubility, and often normal boiling point is replaced by either the well depth parameter from the Lennard-Jones interaction model or the gas critical temperature. It turns out that boiling point is proportional to the Lennard-Jones well depth, and the Lennard-Jones well depth is proportional to gas critical temperature, which is proportional to delta H of vaporization. So there are linear correlations among all of these independent variables, so boiling point, critical temperature, Lennard-Jones well depth, and delta H of vaporization. They're all getting at the point that the higher those parameters are, the more energy there is between penetrant molecules. That is, the greater is the delta H of vaporization, the deeper is the Lennard-Jones well depth, and the more condensable the gas will be, or the greater will be its tendency to condense at a given condition, like around ambient conditions. And so just to reinforce the physical picture, the penetrant dissolution is regarded as a two-step thermodynamic process: condensation of the gaseous penetrant to a liquid-like density, and this is the large step from an energetic point of view, and then mixing these pure compressed penetrant with polymer segments. And if this first step is dominant, then solubility will follow a very simple relationship with critical temperature of the type that's shown at the top of the page. And it turns out that these constants, A and B, although empirical, have values that are quite similar for many different materials, particularly the coefficient that multiplies the boiling point, or if we choose to recast this equation in terms of the Lennard-Jones well depth, the parameter N for many liquids, rubbery and glassy polymers, N has almost a universal value of 0.023 reciprocal Kelvin. And that's remarkable. I'm going to show you an example of that in a moment. And what it says is that the gas solubility in a given liquid or polymer changes very regularly with the Lennard-Jones well depth. Critical temperature also works very well here. And so once you know that you have the solubility of one gas in a polymer, you could use that relationship, this relationship, to calculate the solubility of any other gas you were interested in. The parameter M depends on the details of the polymer, and so it will vary from one material to another, or from one liquid to another. However, for rough order of estimation of solubility, Van Crevelen has suggested a numerical value of minus 9.84 for M. And then this gives you a rough estimate, but a complete model for calculating gas solubility in polymers. Just as a reminder of what the Lennard-Jones well depth parameter is, this is the intermolecular potential energy between two like molecules, for example, two propane molecules or two hydrogen molecules, etc. And that potential energy of interaction is given by the blue curve here. And the attractive part is governed by this parameter epsilon, the so-called Lennard-Jones well depth. And then the size of the molecule is set by the parameter sigma, and R is the intermolecular distance. The deeper is this well, that is, the higher is the value of epsilon, or we often write it as epsilon divided by Boltzmann's constant historically. The deeper is this well, the higher is epsilon, the more condensable a gas is, and the greater its solubility will be in any liquid or polymer. Now, this is a really interesting plot, and it gets at the point that I was making just a moment ago, and that is that solubility often scales linearly or nearly linearly with with Lennard-Jones force constant or with critical temperature. And so we want to look at this closely. The bottom line here is for 100% amorphous polyethylene, and you can see the data points line up very regularly as you go up this scale, higher and higher in condensability. The more condensable penetrants are more and more soluble in polyethylene. You do see one anomaly, and that is that SF6 has very low solubility. It's much lower than one would predict based on its Lennard-Jones force constant. And it turns out, as we'll see a bit later, that hydrocarbon-based polymers and penetrants that have substantial fluorinated character don't mix together well. And this is a phenomena that is also found in liquids. So if you take, for example, normal hexane and try to mix it with perfluorohexane, you'll find that those two materials phase separate and really don't like to mix at all. So fluorinated materials are oleophobic as well as hydrophobic. They don't like organic molecules, and they don't like water. That accounts for some of their unique properties. So the SF6 here is a special case, and we'll come back to that a bit later. And I would say that there's no known explanation, molecular level explanation today about why fluorinated molecules and hydrocarbon-based molecules do not like to mix. There's a couple of other polymers that are shown here with their gas solubilities. Not all the data points are shown, so for clarity. And the thing I'd like you to look at closely here is these last two lines. Here's one for benzene, so gas solubility in benzene, and one for normal heptane. And so these last points are the solubility of these gases in normal heptane. And you can see that these lines are offset from one another depending upon the material, but they all have absolutely the same slope, independent of whether it's a polymer of various sorts or an aromatic hydrocarbon liquid or an aliphatic hydrocarbon liquid. We could put water on the same chart and line up the gas solubility of gases in water, and it would be parallel to these lines. And it's most remarkable that the slope of these lines is independent of the material. And what this is telling us is that once you have established the position of this line vertically, then the dominant factor that governs the solubility of gases, of other gases, is just how far apart they are in terms of their force constant or critical temperature or condensability. This is strong evidence that the first step in dissolution of a gas in a polymer, that is, that condensation step, dominates the energetics of that process. Because what that says is that the solubility depends mainly on how condensable the gas is, independent of the matrix into which the gas is dissolving. It's a very useful phenomena, and one that is, I think, initially counterintuitive and surprising, but what it is getting at is that the more condensable the gas molecules are, the more soluble they are, and that really is is the dominant factor governing solubility of various gases in a given material, be it liquid or polymer. And so this is a slide I think I might have shown you earlier. It's a slide showing data for gas solubility in silicone rubber, PDMS, and also in bisphenol A polysulfone. And you can see that the polysulfone has higher solubility than the PDMS, but that largely the solubility of the gas molecules lie in a very orderly fashion on these lines with critical temperature. Again, higher critical temperature corresponds to deeper Lennard-Jones well depth, higher normal boiling point, higher delta H of vaporization, more condensable penetrant. And the slopes on these lines are also the same. The lines are perfectly parallel. And we often express solubility using this model, where A would be an empirical parameter that adjusts the solubility lines vertically, and B would be the slope of these lines. What's interesting is that slope B is virtually independent of the medium into which the gases are dissolving. And so these are B values from solubility correlations for liquids, rubbery materials, as well as rigid glassy polymers. And you can see that the B value varies very little over the entire range of materials. And that turns out to be an enormously useful fact, because it allows you, once you know the solubility of one gas in a material, it allows you to more or less predict what the solubility is going to be of other gases. And so the bottom line is that the thermodynamics of mixing gas molecules with polymers is similar to that used to describe gas dissolution in liquids, described in terms of two hypothetical steps: condensation and then mixing condensed penetrant with polymer segments. And the energy associated with the first step is often the dominant contribution to the total energy for gas dissolution. And as a result of this, gas solubility often scales with simple measures of gas condensability, which are proportional to the delta H of condensation, things like gas critical temperature and gas normal boiling point. Now, this is the situation in the vast majority of cases that you can run into, but it's not the end of the story. There are cases where one can make the second step more important, and then use that to show deviations in solubility away from the trend lines that we saw a moment ago. You already may have an inkling of this when we saw that the data point for sulfur hexafluoride lay well below that of the other gases that were shown here. We'll come back to that in a moment. And so this approach it works well for solubility of gases when there are no strong specific interactions such as dipole-dipole, hydrogen bonding, etc., between penetrant and polymer. And when these specific interactions become important, then the simple correlation I've just shown you can break down. So, for example, these are old data from Van Amerongen, where he was measuring the gas solubility in polybutadiene polyacrylonitrile copolymers. Now, butadiene is relatively nonpolar, and polyacrylonitrile is very polar. And so when these are copolymerized, as there's more acrylonitrile content in the copolymer, the polymer matrix takes on a more and more polar nature. Now, what this has the effect of doing is as the polymer matrix is more and more polar, It has, in Hildebrand's terminology, it has a higher and higher cohesive energy density. It has a higher tendency to, for the polymer molecules to want to stick together. The energy of interaction between them is stronger. They want to be in greater molecular cohesion with one another. And what that means for penetrant molecules is if a penetrant molecule is going to dissolve into a polymer, there has to be space for it at a molecular level. The polymer segments have to be moved apart in order to accommodate the dissolution of a penetrant. And as those intermolecular interactions between the polymer chains get higher and higher, as you increase the polar content of the material, it becomes energetically more difficult to introduce penetrant molecules into the polymer. And so you see the solubility of oxygen slides down, solubility of nitrogen slides down as the matrix gets more and more polar. On the other hand, the solubility of carbon dioxide, and this is the solubility of CO2 divided by 10, it actually would be 10 times higher than the value shown here. It would be off the scale. Solubility of CO2 actually increases as the acrylonitrile content goes up, because CO2 can undergo a dipole-quadrupole interaction with these polar groups that is favorable and enhances CO2 solubility above and beyond what would be expected just based on the increased cohesion between the polymer chains. So CO2 bucks the trend that you see with gases that can't undergo specific interactions with this particular polymer. Another example is shown here. Polyamides have amide linkages that are very hydrophilic, and as the ratio of amide linkages to aliphatic or hydrophobic linkages in these polymers increases, the water uptake goes up significantly. The final example I'll give is for membranes that are used for CO2 capture and also hydrogen sulfide removal from natural gas today. And it's they're based on the notion that one can design specific interactions that can enhance solubility. And so what's being shown here is CO2 solubility in a variety of liquids, going from N-hexane to dimethylformamide all the way over to methanol. So as you go left to right on this scale, the cohesive energy density, or the solvent solubility parameter, is increasing. The penetrants are getting more and more polar, or the matrices are getting more and more polar as you go left to right. And so what's being plotted here is in the bottom is the CO2 solubility in these various liquids. And you find that in fact there is a maximum in CO2 solubility. As the polarity of the solvent into which, or the liquid into which the CO2 is dissolving, goes up, there is a strong increase in CO2 solubility. However, beyond a certain point, the CO2 solubility starts to go back down, and this is the point at which the cohesive energy density between the solvent molecules like methanol is so high that it actually retards the ability of CO2 to dissolve into the liquid. The methanol linkages or attractive structures are strong enough that they don't want to be broken up by CO2 molecules. But there is a there is a sweet spot in here where CO2 solubility is maximum, and it occurs in the range of structures like tetrahydrofuran, which is an ether-containing material. These ether groups can undergo dipole-quadrupole interactions with CO2, and around acrylonitrile, which is something that we saw in Van Amerongen's work with polybutadiene polyacrylonitrile just a moment ago. And if we plot not only CO2 solubility, but CO2 over nitrogen solubility selectivity, we see that that goes through a similar trend. Nitrogen, of course, cannot enjoy these polar or quadrupolar interactions that CO2 can enjoy with some of the more polar solvents, and so you see a similar trend and can get, in some cases, very high selectivity for CO2 over nitrogen based on solubility selectivity. Now it turns out that including these acrylonitrile units into the backbone of polymer will increase the CO2 solubility, but the interaction between acrylonitrile and CO2 is rather strong, and the acrylonitrile units tend to slow down the diffusion of carbon dioxide more than the solubility is enhanced. And so as you put more and more acrylonitrile units into the backbone of a polymer, you get higher and higher CO2 solubility and lower CO2 permeability, because the CO2 enjoys being in the neighborhood of those acrylonitrile units thermodynamically enough that those interactions are strong enough that they actually slow the diffusion of CO2 through the material. And so materials that have this ether type functionality are often found to have good interactions with CO2 and other gases like ammonia and H2S, but they don't have strong enough interactions to slow down CO2 the way that something like acrylonitrile would be. And we see now similar data, but now for polymers. The data here is all about CO2 and nitrogen dissolving into a variety of liquids, and this is often where I would start in looking for chemical groups that might make useful additions to polymers to enhance solubility of a given species like CO2, for the simple reason that there's enormously more gas solubility data in liquids than there is gas solubility data in polymers. And so and the functional groups that would be on liquids and how they would affect gas solubility of gases provides at least qualitative clues as to how those functional groups would behave in a polymer matrix. So here are the similar plot for CO2 solubility in polymers. The data set is not as clear. This is an ether-containing material, polyethylene oxide. This is a polar material, polyvinyl acetate. And you can see, if you look carefully, that there is a similar maximum to the one that was shown for the liquids. Likewise for CO2 over N2 solubility selectivity. Now, this is showing solubility data for a variety of gases plotted versus the Lennard-Jones well depth. And this is in a block copolymer that contains almost 60 weight % polyethylene oxide. And the ethylene oxide units interact favorably with polar and quadrupolar gases like CO2. And the way we see that is that all of the gases that can't undergo specific interactions with the polyethylene oxide lie on the trend line that we expect between the log of the solubility and the Lennard-Jones well depth. It's with the slope that is the right value that I shared with you a few slides back. But then here's CO2 with solubility way off the line. CO2 should be down here. But in fact, it's several fold higher than one would expect based simply on its Lennard-Jones well depth. And this is a signature of specific interactions between CO2 and the backbone of this polymer. The nylon phase is largely crystalline and has very low solubility for any of these gases, and so it's mainly this polyethylene oxide phase that is that's governing the solubility properties. And so this led us to make cross-linked network polymers that would have a high concentration of ethylene oxide units for specifically for going after carbon dioxide in gas separations. And these types of materials are so-called are hydrogels. The double bonds on either end, these are acrylate double bonds. They're easily polymerized to form network type structures with, for example, thermal free radical polymerization or photopolymerization. It takes just a few minutes to make these in the lab, make polymers out of these. And these cross-linkers can be combined with monomers that have only one of these acrylate units on each side to make structures that have a cross-link network, and then these monomers would act as dangling side chains. And in one case, there is a hydroxyl group on the end, and in the other case, there's a methyl group on the end, so a polar end group and a non-polar end group. The length of the side chain of the ethylene oxide in each of these cases is taken to be about half of the length of the ethylene oxide chain in this cross-linker. And what this means is that as you mix the cross-linker and the monomers in essentially any proportion, you're not changing the weight percent of ethylene oxide, but you are changing the topology and connectivity of the network. The value of 14 in this cross-linker is important. Polyethylene oxide wants to crystallize, and if it becomes crystalline, there's very little gas transport through such a material. And it crystallizes into a lattice that involves 7 monomer units in 3 turns. And so if the length of this run of ethylene oxide gets much greater than 14, say up to 20 or 25, there'll start to be some crystallinity in these materials, and the transport properties will suffer. And so by controlling the length of these PEO side units to about 14, crystallinity is avoided, and is very good for transport properties. And so these materials are all rubbery materials, meaning they're flexible at room temperature, and their glass transition is below room temperature. If you start with just the PEG diacrylate, which is the cross-linker, you can make it into a network polymer. It has a glass transition temperature of minus 40 degrees C. If you start to make mixtures of PEG diacrylate with the PEG acrylate, which has the hydroxyl end group, and to get some dangling chains in that network, the glass transition temperature decreases a bit as you put in more and more and more of the PEG acrylate of this one. However, it doesn't decrease really very much, and we believe what's happening is that in these cross-link network structures, these hydroxyl groups can likely hydrogen bond with other polar functionality that are in these materials, and that these dangling side chains are not really very free to execute much additional molecular motion. On the other hand, if you take this molecule, which is really quite similar, except it has a methyl group on the end instead of a hydroxyl group, and as you add that one into the polymerization with the cross-linker, now you get side chains that are flexible, and they increase the mobility of the polymer matrix, and that decreases the glass transition temperature. And so this family of materials has much greater extent of molecular mobility than this one. And so you might guess what that does to the transport properties. In the family of materials where there's a copolymerization between the diacrylate cross-linker and this hydroxy-terminated monomer, there's almost no change in CO2 or hydrogen transport across the entire composition window of those materials. However, when this more free and flexible side chain material is put into the polymerization, every time you put more of it in, permeability of carbon dioxide goes up, and in this case we can see it going up by a factor of more than 5. So we're getting strong interactions that's favoring CO2 transport, and a highly mobile matrix that favors high CO2 diffusion. At the same time, the selectivity for CO2 over hydrogen is also increasing. That is, as the CO2 goes faster and faster, the hydrogen is moving a bit faster, but it's not seeing as much an increase as CO2 is. And there are separations where one would like to remove CO2 from mixtures with hydrogen and leave the hydrogen behind at high pressure and just remove the CO2 from it. This occurs in the manufacture of hydrogen by steam reforming of hydrocarbons, things like starting with methane and with the water gas shift reaction, reforming methane to make hydrogen plus CO2 as a way to get hydrogen. It's the dominant production process for hydrogen, in fact. And so these materials can be used as membranes for that particular separation. The separation properties, we'll come back to this a bit later, but the separation properties, permeability and selectivity, scale very well with free volume. So these are all the different polymers that I've shown you in the last couple slides, and both permeability as well as selectivity scale with free volume in a way that's quite typical. We'll talk more about that later. And this is free volume determined on a density basis, and this is a measure of free volume from positron annihilation lifetime spectroscopy, which we're going to talk about later. But you see very good correlations between the permeability and the amount of open space in the material. And as a result, these materials have the, at the time they were first published, had the best combinations of CO2 and hydrogen separation properties that were known. And if you can separate CO2 from nitrogen, then it's really CO2 from hydrogen rather, then it's really easy to separate CO2 from nitrogen, because nitrogen is a larger, slower molecule in permeating through these materials. And so these same membranes now have become the standard for carbon capture membranes, and field tests have been run at up to 20 tons of CO2 captured per day, and then another test is planned in the near future for 100-ton CO2 capture per day. Some of that testing is going on at the University of Texas at the J.J. Pickle Research Center. There's a large bank of these membranes that are at the pilot plant at the Pickle Research Campus that are undergoing testing for carbon capture. Now, we've just talked about a few examples where the presence of specific groups in polymers enhances the solubility of one particular species. It also turns out that this effect can operate in the other direction. I mentioned briefly that hydrocarbons and fluorocarbons don't like to mix. And this is true in the liquid state as well as in gases dissolving in polymers. And so what's being shown on this slide is the solubility of a variety of gases in polydimethyl siloxane on the left, correlated with critical temperature. And you can see that for all of the light gases like hydrogen, oxygen, nitrogen, all the hydrocarbon gases, they lie right on this trend line with solubility. In critical temperature, the slope is exactly what we saw previously. And now look at these guys. Here's CF4, perfluoroethane, perfluoropropane, well below the standard line for all the hydrocarbons and other light gases. And so this is an indication that there are factors that that do not support the mixing of these fluorinated compounds with hydrocarbon-based polymers. And the origin of this at a molecular level has never been completely explained and is still an open question in the literature, but it is a fact. What's shown over here is the solubility isotherm, or concentration of gas dissolved in silicone rubber as a function of pressure for ethane and perfluoroethane. You can see a vast difference in the uptake of gas in this hydrocarbon-based polymer, whether you're dealing with a hydrocarbon-based gas or a fluorinated gas. And this phenomena is useful in the sense that we can also see this trend in opposite fashion when membranes are made from perfluoropolymers. And so we can make perfluorinated polymer membranes, make these same measurements. And what you would find in that case is that the fluorinated penetrants would lie on the line, but the hydrocarbon penetrants would lie below the line. And that provides a basis for restricting the solubility of hydrocarbons into fluorinated polymers. And this has been proposed by some as a way to improve the performance of membranes for hydrocarbon separations, like separating ethylene from ethane or propylene from propane, because those gases will dissolve to a very limited extent in fluorinated polymers as opposed to hydrocarbon-based polymers. And if they dissolve to a low extent, then they have less tendency to alter the transport properties of the membrane in ways that are unfavorable, so-called plasticization phenomena that we'll talk about later. You also see them applied in medical applications. This particular principle, gases like SF6 and perfluoropropane are used in eye surgeries, in particular in vitrectomies, which is repair of detached retina. And in that surgery, the fluid in the eye is removed and laser repair of the detached retina is undertaken. And at the end of the operation, the eye is injected with either SF6 or perfluoropropane, and this keeps the wound stable and keeps the eye from collapsing until the body can generate new fluid to fill up the eye. And over time, the SF6 or perfluoropropane will gradually, slowly dissolve into the largely hydrophilic and oleophilic tissues that surround the eye. And it's their low solubility that in those tissues that causes their their dissolution to go slowly enough to act to prop the eyeball in shape structurally, and to allow the apply pressure on the retina that's been wounded until it can heal. And then gradually over time, these gases dissolve into the body, and the normal eye fluid replaces them. But their low solubility and therefore low rates of transport out of the eye put them in to be there in the right time frame to help the healing take place. Here's another view of the low solubility of fluorinated gases in hydrocarbon-based polymers. And so this is now a much more extensive correlation of gas solubility data in silicone rubber or PDMS. And it's now data taken over a number of penetrants and at many different temperatures. And when temperature is varied and you want to combine gas solubility data on a single plot, one of the proposed ways to do that in the literature is to plot the solubility versus the critical temperature divided by T squared. And you can see in this case there's a very nice correlation over a wide range of solubilities. And the outliers again are the fluorinated gases. They're well below where you would expect based on the measurement temperature and their critical temperature. Again, emphasizing this notion of like dissolves like, and unlike does not dissolve unlike readily. So with that, we'll end this lecture, and we'll pick it up next time with lecture notes 8. Thank you.